So as I am recording these podcasts on monsoon extremes in August 2021, IPCC, the Intergovernmental Panel on Climate Change, has started releasing the assessment report 6. So it makes sense that we pay little attention to what the AR6 or CMIP6 models are saying about the extremes. I'll start by talking about the scenarios that are being used in CMIP6, which are different, slightly different than the AR5, Assessment Report 5 and CMIP5. So we are looking at here the so-called RCPs, representative concentration pathways, that were used in AR5, CMIP5, but there were also developments of the shared socioeconomic pathways after AR5 was done in terms of modeling, but AR6 now includes a combination of RCPs and SSPs, and we will just go through them quickly. This is not the place to go into the details, but we should be aware of what was done. So here, as you probably remember, RCP 2.6 is the most benign scenario for staying below 2 degrees C, which was then updated with the 1.5 C assessment. So 2.6 is the watts per meter squared energy imbalance at the top of the atmosphere by 2100. If we follow that concentration pathway, then you similarly have 4.5, 6, and 8.5, where 8.5 is the baseline, no policy scenario or business as usual. And we are looking here at a time period going from 2000 to 2100. And you can see the emissions in terms of gigaton carbon for each of these scenarios with a range. It's a combination of using integrated assessment models, climate models, or system models, and sometimes iterations to produce these future evolutions or trajectories. So those bands come from there. So I will say that and leave it there, but you also have similarly scenario for future scenarios for the future in terms of methane emissions and N2O emissions, the other two major greenhouse gases. As we said before, when we think about greenhouse gases, we have to worry about the concentration, which matters, the lifetime or residence time, which matters, and of course the global warming potential. How much more global warming a greenhouse gas will produce compared to CO2, which is used as a reference of 1. So methane, for example, is about 25 times more global warming potential than CO2 over a period of 100 years. It's done by weight, by molecules. There are all kinds of details. N2O, I think, is a couple of 100 times, if I remember right. Residence time of CO2 is multiple centuries. Methane is about a decade. N2O is, I think, about a couple of centuries as well. So keeping those things in mind, there were also shared socioeconomic pathways developed, which looked at not just concentration pathways, renewable energies, what else? Population, GDP, etc., policies, and so on. But they also considered other social adjustments like mitigation and adaptation, with pathways that use rapid growth, regional rivalries, and how they may affect the climate evolution of climate action, inequality, and sustainability. So here you have two axes. One is mitigation heading up this way to high challenges. In this direction, mitigation has low challenges, and here adaptation challenges are low, and here adaptation challenges are high. So you ended up with 5 scenarios. This is the sustainable scenario with net CO2 emissions showing the corresponding trajectories, and as you go in this direction, adaptation challenge is high, but mitigation challenge is still low. So you end up with inequality. And regional rivalry gives you these ranges of temperature warming, these ranges of CO2 emissions, and rapid growth obviously gives you much higher emission pathways, especially in the baseline, and then the various resulting energy imbalances. Okay, so obviously anytime you drop below net CO2 of emissions of 0, you are making great assumptions about carbon capture sequestration, negative emission technologies. It's not that you are not emitting carbon dioxide, it's just that you are taking out more than you are emitting. So middle of the road scenario has balance of mitigation and adaptation strategies with a range of scenarios and warming. Okay, so what CMIP6 has done is combine the CO2 emissions with SSPs, so they end up with different set of scenarios when you look at the CO2 emissions in gigatons here, going from historic period to the future. So you can see that business as usual still goes up here. Now this is SSP5 8.5, so it's a combination. And then you have newer scenarios which are like SSP4 and 6, SSP1 and 1.9, and so on. And there is also a SSP5 3.4 OS, where OS is the overshoot scenario. Again, you can look up the nice descriptions given in this report from Carbon Brief, which is where I took the figure from, which itself comes from the IPCC protocol development and related reports and papers. Okay, so this is what we are looking at in terms of historical simulations and future projections. So we will look at the CMIP6 rendered historic simulations of extremes and future projections in terms of monsoon extremes. But in the meantime, these various scenarios of SSP1 and radiation balance imbalance combinations give near-term, mid-term, and long-term warming projections in terms of best estimate and very likely. So very likely changes the probabilities of hitting the targets. So as we said before, one also has to keep in mind that in the near term, model uncertainties tend to dominate, but when you go to long term, the scenario uncertainties dominate in terms of mitigation challenges, adaptation challenges, regional rivalries, population, GDP, renewable energies, carbon capture technologies, bioenergy, and carbon capture sequestration, and so on and so forth. But you see the range here. The best estimates for all of these remain in the 1.5 range, less than 2 degrees, even though the very likely range is larger. And by mid-term, that's by in the near term, which is still good news, by the way. So overshoot will happen, but it's a question of how long the overshoot will happen and when we will come back and what the consequences will be in terms of remaining in the overshoot of 1.5 or 2 degrees. So by midterm, we're going to cross 2 degrees, and by the long term, the worst of the scenarios is going to be high at 4.4 best estimate, with a likely range of 3.3 to 5.7, which is quite a large range. Before we go to the extremes, we also have to understand the climate sensitivities, which is, I think most of you know, idealized calculation where you double the CO2 at some rate and you keep it there for a long time till the system equilibrates, ocean, land uptake, atmospheric storage, and all the dynamic, thermodynamic adjustments, and so on. The AR5 range was 1.5 to 4.5. So that's including the scenarios, and that's the range of model sensitivities. CMIP5 models themselves had a slightly narrower range, and CMIP6 models have a broader range here. So the understanding of climate sensitivity, especially because of the feedbacks in the system, goes up, but the model uncertainties still give you a range of, or model formulations, let's say, in terms of convection, clouds, land use, vegetation representation, land ice, and so on, give you a range of climate sensitivities. That is something to remember, because when you look at the projected changes going from historic period to, so this is still historic, not projections. You are looking at observed CMIP6 and CMIP5 with different number of models. These numbers are number of models which are showing the range here. And you probably also know that the CMIP5 models and CMIP6 models are in general climate models forced with observed solar variability, volcanoes, greenhouse gases, aerosols, and so on, do not produce year-to-year variability, but they are very good at producing the forced variability or the trend. So models have El Niños, but this is not a prediction. So a given year, for example here, the observations may produce an El Niño and a global change in temperature, but the models don't necessarily have El Niño in the same year. They will have a frequency of El Niños, changing frequencies, amplitudes, durations, etc., which is their internal variability, but that doesn't necessarily match year by year to observed variability, because it's not an initialized integration which can maintain exact match with observations. So what we look for is whether models are able to reproduce the trends observed, and you can see that the so-called warming pause was not captured by the models, so the warming is a little bit higher, but by now, by 2020, the models and observations are again together. But more importantly, the difference between CMIP5 and CMIP6 is not that great. But when you look at historical trends for different periods, so here's the observed range for 1880 to 29 and 1970 to 2019. So the warming itself is accelerating, so you can see the increase in observed periods, observed data as well, estimates. CMIP5 had this range, and CMIP6 models are closer but still a larger range in different models. When you look at the more recent period of 1970 to 2019, observed warming is here, CMIP5 are here, and CMIP6 models are here. So this is corresponding to the sensitivity that we looked at as well in terms of the range of models and their warming. So that you can see here as well. Okay, so those kinds of details matter. I'll come back and discuss a little bit about biases from convective parameterization, because before we look at projections of extremes in CMIP6 models, we have already talked about model biases and uncertainties and differences, but it's worth looking at again a little bit about how convective parameterization, which is a necessary evil in the coarse resolution models or even in high resolution models, because the understanding of explicitly representing convection is still not complete and process understanding. So parameterizations are often necessary, especially at coarse resolution, but there are high resolution convection permitting and explicit convection models. There are also cloud resolving models and so on, but they are very high resolution. They cannot be integrated for such long periods, and there are other issues in terms of validation, evaluation, just analysis of the amount of data they will produce at that resolution, and so on. So I'll come back and do that in the next podcast, but this is a quick introduction to the scenarios and climate sensitivity and observed warming rates produced by CMIP6 models versus CMIP5 models. After looking at the impact of convective parameterization on extremes, we will go back and look at how CMIP6 models are projecting extremes and droughts. Okay, that'll probably conclude the series of podcasts, even though in the last one I said I already concluded. Okay.